Feedstocks for polymerization of ethene to produce polyethylene need to have a purity in excess of 99.95%. Such purities are achievable in distillation separations. However, the distillation columns need to have a large number of trays, about 100 or so, and these are operated at high reflux ratios because of the small differences in the boiling points between ethene and ethane. The relative volatility is relatively low, about 1.2. In order to reduce the energy costs associated with ethene-ethane distillations, several developments in metal organic frameworks have targeted this separation in order to develop MOFs that are suitable for this separation tasks. There are basically two types of metal organic frameworks that are capable of separating ethene and ethane mixtures. The first class of metal organic frameworks are selective to ethene. In this category of ethene selective MOFs, we have two subcategories, one exemplified by magnesium MOF 74 or iron MOF 74 or cobalt MOF 74 that consist of hexagonal one-dimensional channels with unsaturated metal sites at the vertices of these points as indicated in blue. The uptakes of both ethene and ethane are high, and the selectivities are also of the order of 20 to 30 or 40 depending on the metal used. Typical breakthroughs for iron MOF 74 are shown here in the red circles. We note that the there is a considerable time delay before ethane breaks through, and much later we have the breakthrough of ethene. A different class of MOF is exemplified by UTSA 280, which operates on the principle of size exclusion of ethane. There is a subtle difference in shape between ethene and ethane. Ethene is basically a two-dimensional molecule, and by tuning the shape of the pores, these pores of UTSA 280A can be made to only accommodate ethene while excluding ethane. So we have two different breakthrough characteristics, one in which ethane is almost completely excluded from the pores, and another class of MOFs in which both gas components have finite uptakes within the pores of the metal organic framework. In PSA separations to produce purified ethene, it is preferred to have MOFs that are not only selective to to ethene, but ethane is completely excluded from the pores. And I will explain this in the next slide. Here is a schematic of a 4-step PSA scheme for producing purified ethene using an ethene selective MOF. The 4 steps consist of a pressurization step, followed by an adsorption cycle in which the products leaving at the top of the fixed bed adsorber consist of purified ethane. This is followed by co-current purge, in which a portion of the product ethylene from the final blowdown step is used to purge the ethane that is present within the pores and in the void spaces, and the purged gas mixture is collected and fed along with the feed mixture to the adsorption cycle. The co-current purge phase is followed by the final 4th step that consists of countercurrent vacuum blowdown. Any ethane that is present within the pores or in the void spaces contributes to the impurity of the product ethene, and therefore in principle it is preferable to have a MOF in which ethane is completely excluded from the pores, and that is the case with MOFs such as UTSA-280A and cobalt gallate. The achievement of high purity ethene meeting the feedstock requirements to polymerization reactors is more easily achieved using adsorbents that selectively adsorb the saturated alkane. One such example is a hydrogen bonded organic framework that is described in the recent paper in Angewandte Chemie 2023. This HOF-NBDA has a pore surface that is non-polar, and such non-polar surfaces are beneficial for high C2H6 selectivities. The adsorption breakthrough curves are shown here, where C2H4, the less strongly bound adsorbent, breaks through earlier and can be recovered in the adsorption cycle to the required level of purity.